Good morning. So we'll be continuing with module number 6 waveguides in this lecture also. So in the last lecture, we have derived the expressions for the component of electric field along x, y, the component of magnetic field along x and y. And we saw that the component of electric field along any direction other than the direction of propagation depends on the component of magnetic field along the direction of propagation, which is Z, and the component of electric field along the direction of propagation. Okay, so Ex and Ey or Hx and Hy has its dependencies directly to the component Hz and Ez. So if you look at all these equations, you can see that all the equations depends on Ez and Hz. Now, if the wave was propagating in, let's say, x direction, then instead of Hz and Ez, you would have Hx and Ex. And instead of Ex, you will have Ez. Instead of Hx, you will have Hz. So the most important component in this case, when the wave is propagating, when the electromagnetic wave is propagating, is the component of electric and magnetic field along the direction of propagation. Okay, so this I have already told earlier that it means that if you are in a waveguide and this is how the wave is propagating, for example, in this direction, which is said, the component along the Z direction means that the electric field is still perpendicular to the direction of propagation. But the component, or if you resolve the electric field and magnetic field in directions perpendicular to each other, then you can see that there will be one component along the direction of propagation. Now, I am saying that in waveguides, it might be possible that this component will not exist. It might be possible. So if these two components doesn't exist, then there is no wave inside a waveguide. If both, I'll repeat it again, that's an important statement. If both electric and magnetic field components along the direction of propagation doesn't exist, that means if Ezx is equal to Hzx is equal to 0, that means there is no electric field and magnetic field existing inside the waveguide, or there is no electromagnetic wave inside the waveguide. Okay, so let me write it down. I'll write it as different conditions. Okay, let me choose a different color. Okay, so the first statement is like this: Ezx is equal to 0, that is equal to Hzx. That means both electric field and magnetic field components along the direction of propagation is 0. If that is the case, if you substitute this in these equations A, B, C, D, you can see that all the values of Exs, Eys, Hxs, Hys is 0, which means there is no electric and magnetic fields, which means there is no electromagnetic wave. This is inside waveguide. Okay, so the electromagnetic wave will exist in an unbound medium when these components are 0, but inside a waveguide, this will not exist. Okay, that means if and this has a special name called as transverse electromagnetic wave, or TEM. Okay. Now here you should note that there is no electric and magnetic field along the direction of propagation. The electric field and magnetic field exist, but it will exist in direction perpendicular to the direction of propagation. It will not, there will not be an electric and magnetic field component along the direction of propagation. And if that is the case, then in a waveguide, there will be no electromagnetic wave. So if there is no component along the direction of propagation for electric and magnetic field, such a wave is called as transverse electromagnetic wave. Now here you should note that transverse, the name means it is basically means perpendicular. So it says perpendicular electromagnetic wave, which means electric field and magnetic field are perpendicular to the direction of propagation. So this implies E and H are perpendicular to the direction of propagation. But if such case, so this wave can exist in an unbound medium, for example, in free space, but this wave cannot exist in a waveguide. That's a very important point. Okay. This is also called as TEM mode. We are going to study about different modes. So this is also called as TEM wave or TEM mode. Now the second situation is when, let's say, my electric field is 0 and magnetic field is not equal to 0. So if you substitute that in equations A, B, C, D, even though the electric field is 0, for example, this is 0, this is 0, this is 0, this is 0, you still have an equation with the magnetic field which is not 0, which implies that you have a wave existing inside a waveguide. So this is 0 implies there is no electric field component along the direction of propagation. But there is a magnetic field component along the direction of propagation. Okay, which means that, for example, if you are in a waveguide and the wave is transmitting something like this, this is your Z direction. So the wave is transmitting along the Z direction. It is moving along the Z direction. Now EZS equal to 0 means basically you have an electric field which is perpendicular to the plane of paper. For example, it is now pointing towards you. So now it doesn't have a component along Z. Your magnetic field might be in some direction like this. Okay, and if you resolve this, you see that it has two components. One along Z, although it is along minus Z, but there is a component along the direction of propagation. Okay, so this kind of wave is called as transverse electric wave or mode, TE mode. Okay, so this can exist inside a waveguide. So this TE mode exists inside waveguide. Okay, now there is one more condition where you say your electric field component along the direction of propagation is not equal to 0 and your magnetic field component along the direction of propagation is equal to 0. That means I have the waveguide. The wave is propagating. Your magnetic field component is now perpendicular to the plane of paper, and your electric field component is now at some angle to the direction of propagation. So this electric field component now can be resolved into two components along along z and arbitrary direction. So now you see that the electric field has a component along the direction of propagation. Okay, so let me mark this. This is E. Here also this is E. This is H. Here also this is H. Okay. Now in this case also, if you substitute that values here, Hzx is 0. Here also Hzx is 0, Hzx is 0, Hzx is 0. But because of the presence of this part of the equation, you will have a value for Exx. Because of this part, you will have a value for Eys. Because of this part, you will have a value for Hxs. And because of this part, you will have a value for Hys. Because of which the wave will exist inside a waveguide. So this mode or this wave is called as transverse magnetic mode or wave, both are same, or it's called as TM mode. And TM mode exists inside waveguide. Okay, so these are the three important modes of propagation inside a waveguide. And the important thing you should understand is that TEM mode or TEM wave will not exist inside a rectangular waveguide. That's a very important result, which was asked in many times in gate exams also. Okay, now there is one more mode. Actually, we are not concerned much about that, where Ezx not equal to 0 and Hzx is not equal to 0. This is called as a hybrid mode. Okay, it's called as HE mode. We will not look too much into this hybrid mode, but we will be looking in depth for transverse magnetic and transverse electric mode. Okay, so these are the important results from the equation that we have derived in the last class. And just to complete this equation, the value of H square is equal to gamma square plus omega square mu epsilon. Okay, so this can be written as gamma square plus some constant k square. Fine, and I can still write it in a form as kx square plus ky square, because your wave is the electric and magnetic field that you have found is along x and y direction. So I can write h square as kx square plus ky square. Fine. Now, next what we are going to do is we are going to find out what is the actual expression of Hzs and Ezs. If you can find out the expression for Hzs and Ezs, then we can substitute that in this equation, and we can find how the wave looks in x direction. The electric field looks in x direction, similarly in y. The magnetic field, how does it look in x direction, and similarly in y. So next we are trying to derive the expression for Hzs and Ezs separately for TM and TE modes by applying boundary conditions. Okay, so that's what we are trying to do in this class. So first we will look at a general expression, and then we will go to specifically for TM mode and TE mode. Okay, fine. So before going into that, I just need to revise one part. So I derive the equation from an older derivation, that we have discussed in the class. I think you might have forgot all this. So I just write the initial few steps of that derivation, and we will then jump to our original derivation. Okay, fine. So let's start with Maxwell's equation. So everything starts with Maxwell's equation. So from Maxwell's equation, and the derivation for T and TM mode has asked in almost all the exams, including supplementary, including regular, either TM or TE. So both derivations are very important, and you have about 90% chance that you will get one derivation in the exam. So please be careful. Okay. So from Maxwell's equations, you have del cross E S. So I am looking at phasor is equal to minus j omega mu Hs. Also, del cross Hs is equal to sigma plus j omega epsilon into Es. Now, we have already assumed that the media inside a waveguide is lossless. Which means the conductivity is equal to 0. So I can write del cross Hs is equal to j omega epsilon Es. Fine. Okay. Now let's do del cross Es. So this is equal to minus j omega mu, which is same, into del cross Hs, because the only vector part is Hs, so you can take del cross inside. We will use an identity which says del cross A is equal to del dot A minus del square A. This is an identity. Okay. So if you compare these two equations, you can say that your A is actually Es. So I can write del cross Es is equal to del into del dot Es minus del square Es is equal to your right hand side j omega mu into del cross Hs. Now we have assumed that the media is source free. This assumption we have defined in the last class itself. The media is source free implies the value of rho v is equal to 0. And you know that del dot Es is equal to rho v, which is equal to 0, which means that this part will be equal to 0. So I can write del square Es minus del square is equal to minus j omega mu into del cross Hs. Now del cross Hs is j omega epsilon Es. So this is equal to minus j omega mu into, which is this one. I substitute it here. J omega epsilon Es. Okay. Now this is equal to j into j is minus 1, minus 1 minus 1 plus 1, omega square mu epsilon Es. Okay. Now you can multiply it with minus sign. So this is actually gamma square ES, which we have already studied, where gamma is equal to omega into root over mu epsilon. So I can write del square ES minus gamma square ES is equal to 0. Okay, so this is one wave equation actually we have derived in previous class. Similarly, you can also derive del square HS minus gamma square HS is equal to 0. Okay. Now let me make a small correction in that equation. Let's say I say del square ES plus K square ES equal to 0 and del square HS plus K square HS is equal to 0, where K is equal to minus gamma. And the magnitude of K will be omega into root over mu epsilon without the sign. Okay. Now let's consider only the equation for electric field, which is del square ES plus K square ES is equal to 0. So let's consider only this equation. Now you see that ES has components like EXS, EYS, EZS. When you do del square of these components, basically you will have three equations from this single equation. Okay, because you do del square EX plus K square, del square EXS plus K square EXS, that is equal to 0. That is one equation. That is del square EXS plus K square EXS equal to 0. Then del square EYX plus K square EYX equal to 0. Then del square EZX plus K square EZX equal to 0. So you can get three different equations. But we are concerned about only one such equation, which is this one. Why? Because our aim is to find an expression for EZX. We are not concerned about what is there for EXS or EYS because we already know the equation in terms of EZX. So we are concerned about only EZX. So I write the equation for only for EZX. So del square is dou square by dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So I can write this equation as implies dou square EZS by dou x square plus dou square EZX by dou y square plus dou square EZS by dou z square plus K square EZX is equal to 0. Okay, these are not vectors actually; these are components. Okay. Now we want to solve this equation, and we want to get the value of what is the value of EZX. So we need to solve. Let me mark as equation number 1 to get the value of EZS. Now, how will you solve this equation? Now, we are going to solve this equation using variable separable. Okay. So what we are going to do is we are assuming that let EZX, which might be a function of x, y, z, equal to x of z, x of x into y of x into z of x. Sorry, y of y into z of z. So x of x is a function of x, y of y is a function of y, and z of z is a function of z. And we assume that all the three x, y, z are independent. If they are independent, I can separate them out. That's what we have seen. So we are assuming that, okay, this is my solution. And then we are going to find out what is the value of x, y of y, and z of z. Okay. So now let's substitute this equation, which is equation number 2, in 1. So substituting 2 in 1. Okay. So instead of writing x of x, I'm just going to write only x. Instead of writing y of y, I'm writing y. Instead of writing z of z, I'm writing z. That's all. Okay. So when you substitute it in equation number 1, the first term is differential with respect to x, so that y and z will be constant. The second term is differential with respect to y, so that x and z will be constant. And the third term is differential with respect to z, so that x and y are constant. Okay. So I can write this as x double dash into yz plus x into y double dash into z plus x y z double dash plus k square x y z is equal to 0, where x double dash is dou square xy dou x square, y double dash is dou square y by dou y square, and z double dash is dou square z by dou z square. Okay, that's equation number 3. Now let me divide equation number 3 by xyz. Implies I can write as x double dash by x plus y double dash by y plus z double dash by z plus k square is equal to 0. So why I did that? Because I want to make sure that each term is a function of only one variable. So if you look at here, this is a function of x, y, and z, because x is a function of x, y is a function of y, z is a function of z. Similarly, each and every term. Now I want to make each term as a function of only one variable, so that I can separate them out. So what I did, I divided by x, y, z. So here, this is a function of only x, this is a function of only y, this is a function of only z, and this is a constant. Separate out. Okay. Now, since the variables are independent, each term of this equation, each term of equation 4 must be a constant. Because the variables will not depend on each other, the solution also makes sure that there won't be any combination of the variables, which means each term in the equation number 4 is a constant, which means x double dash by x should be a constant, which let's say it is minus kx square. I just put minus because our solution will be easy. Similarly, y double dash by y is equal to minus ky square. And for x, z double dash by z, the value is gamma square, which we have already seen from the equation. okay, because it is in the direction of propagation. So now I have three equations. The first equation is x double dash plus kx square x equal to 0, y double dash plus ky square y is equal to 0, z double dash minus gamma square z equal to 0. So you have three equations, and we can solve all the three equations easily. Each of this equation is a second order first degree equation, and you know the solution of this equation. I'm not going to derive the solution. The solution of the equation is, for equation number, let's say I number this as 1, 2, and 3. So in 1, the solution of x will be something like C1 cos kxx plus C2 sin kxx. Y will also be similar because both equations are of similar form. So this y will be C3 cos ky plus C4 cos ky sorry, not cos, it is sine. And the last is z of z is equal to, now here the equation is having a minus sign, because of which instead of getting a cosine or sine function, you will get an exponential function. So C5 e raised to gamma z plus C6 e raised to minus gamma z. And your expression for, so this is equation for equation number 2, and this is for equation number 3. So your expression for E zx of x comma y comma z is equal to x of x into y of y into z of z, which is equal to C1 cos ksx plus C2 sin kxx multiplied by C3 cos kyy plus C4 sin kyy multiplied by C5 e raised to gamma z plus C6 e raised to minus gamma z. Now this is a very lengthy equation. We need to make sure that we can simplify this equation, but by using boundary condition, that is okay. Okay, and similarly, now in this equation there is a catch. Now you see that the wave is propagating in z direction. Okay, so there's a z axis, and the wave is propagating in z direction like this. Okay, so wave might start from z equal to 0, and it keeps on going. So maybe when it reaches, let's say, very high value, z equal to infinity, it can wave still exist. Now, when you have value of z increasing, the z value here also increases. So basically, this z is actually where the current position of the wave is in the z axis. Now, when you increase z, this also will increase. When the wave reaches, let's say, infinity, this will become infinity, which is not possible, because when this is infinity, the whole term is infinity, which means the electric field become infinity, which is not possible in any condition. That means this term will not exist, or you can say or I can write a reason that the wave has to be finite at infinity. That is, EZS is equal to or it should be less than infinity at z equal to infinity. Implies C5 is equal to 0. So I can write my equation as EZS of x comma y comma z is equal to C1 cos kxs plus C2 sin kxx multiplied by C3 cos kyy plus C4 sin kyy multiplied by, you will have the constant C6 e raised to minus gamma z. That's all. The other term will not exist. Okay. So the reason we should understand that when the wave is infinity, the value of the wave should be finite. If that term exists, C5 e raised to gamma z, then the value of the wave will become infinity. The value of the electric field will become infinity. So that condition is not possible. So we will make sure that C5 is equal to 0. Similarly, the value of hzs of xyz will also be something like b1 cos kxx plus b2 sin kxx multiplied by b3 cos kyy plus b4 sin kyy multiplied by b6 e raised to minus gamma z. Okay. So this is the general equation that we have derived. Now what we are going to do is we are going to apply boundary conditions to this equation for each TM wave and TE wave. And then we are going to see what is the final expression of electric field for a TM wave and for a TE wave. Okay. So let's do that. I think it will not take too much of time. So for transverse magnetic mode, or TM mode, for TM mode, the value of Hz is equal to 0. Okay, that's the condition for TM mode. The value of Ez or Ezs is not equal to 0. Now, our waveguide is something like this. Okay, so you have an axis here. Okay, this is X, this is Y, and you have the 0, 0 here, 0, comma A here, and 0, comma B here. And you see that for a waveguide, the outer structure is metal. And inner thing is some lossless dielectric. So there is a boundary at this ends of the waveguide. For a metal, you know that the conductivity is infinity, but the electric field is equal to 0. Electric field will not exist inside a metal. That we have already seen. Metal is basically a conductor. So we are going to apply this boundary condition and we are going to find out what is the values of Ez and what is the expression for EZS for a transverse magnetic mode. We substitute that expression in our EXS, EYS, HXS, and HYS, and we'll see what are the corresponding expressions. So I think that will take some amount of time to derive this. So we will stop it here for today, and we will continue with the same notes in the next class so that we will not lose our continuity. Okay, fine. So let me just take the attendance.